then now we can be good to go. So thank you for the messages. Yes, fine. So now I hope you can see my screen. I've already shared it. We are on these slides on linear systems. So far we have been revising. We have done all this here. So if I may reopen, where is that? Yes, so we started by talking about machine learning. We revisited the introduction that we had started on in AI. Then let me record this one. Hi. Then we are revising. No, we checked learning, understanding statistical machine learning. So we are currently here, and to be able to understand statistical machine learning, we are doing some revisions. So be that as it may, we have already talked about statistics and probability. Then now we are talking about linear algebra. Then today we'll finish by talking about calculus. So last time we talked about linear algebra. We already talked about vectors and matrices. And today we are here on linear systems. Then I will share the videos. So now there's this thing called linear systems. I hope you have already gone through this and revised. Here is how matrices and vectors are actually kind of interacting in order to get other vectors. Pictures like this, and also with vectors, which looks like this. So also, as we'll be dealing with a lot of matrices and vectors, and this idea of linear systems is going to be important. So last time we checked on how to find the inverse of a matrix, and we saw there's something called a determinant, which we actually revised, okay, the determinant of a matrix. So if a matrix has no determinant, actually it has no inverse. And the reason why we need the inverse of a matrix is for equations like these ones that can be actually used to solve linear systems. So from a linear system that looks like this, a system of linear equations, you can form a coefficient matrix by taking the coefficients. We'll do this down here. Then you can actually be able to get its inverse and then solve the equation. So quickly, this one's it's for you to revise, but if I may just mention, there are two ways to solve linear systems. There are other ways like graphing, etc. But Cramer's algorithm and Gaussian-Jordan elimination, these are the main ways. So Gaussian-Jordan, Jordan, you should actually know it, and then maybe see Cramer. You won't be able even to see it, but it is part and parcel of the algorithm that you're implementing. So an example is here. This is how Cramer's works. You have a determinant of the coefficient matrix. Then you have to form another matrix from the coefficient matrix by replacing a column. So for example, if you're given this one, I don't know, this one is not clear. So for example, you're given, yes, 2x1, etc. You can see this. You on your end, you can be able to see this one. So if I may maybe put them side by side. So actually, you can be able to solve this one by forming the coefficient matrix. So I'll just form a coefficient matrix right here on my right very quickly. Then the rest you can revise. So -2, 3, -1 will be the first row, 1, 2, -3. So this is the matrix we are looking at. Then -2 down here, -1. You're just taking the coefficients and 1. Okay, so this one becomes the coefficient matrix of this linear problem. Then this coefficient matrix, you find its determinant like we did last time. So you can refer to the workings here. Then later on, you'll form another matrix, the way Cramer's algorithm works. For example, to form a matrix called A sub 1. So according to the definition here is that you form the matrix from the original coefficient matrix by replacing its ith column, okay, by y. So y is actually this target that you have here. So instead of -2, 1, -2, you will just form a new matrix with that new column. So it will be now 1, 4, -3, then 3, 2, -1. The rest remains -1, -3, and 1. Then you also get the determinant of this one. Then to get the first solution, A1, you just divide the determinant of A1 to. So you can actually try to solve for x2 and also for x3. And you will have revised Cramer's algorithm. But Cramer's is still computationally expensive because we said computing determinants of matrices beyond order 3 is very, very expensive. So Gauss-Jordan elimination is like the most efficient way. This one, again, you have to revise how to reduce a matrix into row echelon form and also how to do back substitution. So quickly, I'll just mention these ones are very easy. There's an example here. The matrix is being reduced. So when a matrix is in row echelon form, it normally looks like following. So let's say for a 3 by 3 matrix, the first row, you will force it to start with 1. Then you can have any other values there. Then the second row should start with 0, followed by a 1, followed by anything there. Then the third row can start with a 0, followed by a 0, and then you can have a 1 here. Should have a 1 here. No. Okay, fine. Yes. So when a matrix is in this form, it is called row echelon form. Then we can actually use this matrix to solve a lot of things. So how do you force matrix to be to look like this? You use a series of what is called elementary operations. Like, for example, you transform the rows into new rows. For example, you can see here, though it is a bit tiny, so refer to your notes. You see here, I have said I did -2 row 1 plus 2 plus row 2 to get the new row 2. In other words, I'm just taking -2 multiplying by whatever value I have in row 1. So here -2 times 1 is 2. Then I get my new row 2. So I am transforming this second row, okay, until finally I have this format. Then it is this format that you use it. So you refer also to what we have here. Then that is how Gauss-Jordan elimination actually works. So quickly, my interest will be here before I finish this linear algebra. We won't take much time here. So I hope also you watched the video, the link that is there that I said it's compulsory that you watch this link that is actually here. Okay, so if you have not watched that one, please, after this class, you need to watch that one. So what do matrices actually do? Why are they so interesting is that matrices are able to do a lot of things to vectors. Most of these things are geometrical transformations. It means that a vector could be made to form another vector. So we call these transformations. So they can either be rescaling or rotating or doing some nice things to vectors in order to get other vectors. Sometimes they can take a vector from a two-dimensional space and take it to a three-dimensional space or vice versa. So anytime a vector or a matrix is found in a two-dimensional space, we are always going to write that one as R2. Okay, so we say the matrix or the vector is spanning R2. We actually mean it is a two-dimensional space. Sometimes you can have the R written like this. Okay, that's a two-dimensional space. If it's three, it is a 3D space, and so on and so forth. So there is this thing called linear independence as far as vectors are concerned. So, and this is going to be important because it is just a way to describe the relationship between vectors. So the easiest plane to draw is always a 2D space. And it's always 0 here, the origin. So vectors look like this. They have a direction. So let's say this is a vector. Then there's another vector that looks like this on the same. Okay, so maybe that other vector is a bit longer. And maybe there's another vector going the other way around, etc. So these vectors are related in some way because they are kind of found across a similar line. So having vectors being related is actually going to be important because even between this point and this point, whereby we count like this, so x-axis, let's say the value here is 2, and then y-axis, let's say the value here is 3. So we normally just write vector 2, 3, like this. So within the space of vector 2, 3, which is from here to here, okay, there are other smaller vectors that can be defined. In fact, infinite vectors that can be found here. All these vectors we can ignore and just concentrate on this vector, given the principle of linear dependence. Okay, fine. To cram this much again, like we said last time. So linear independence, you can read all the way here, how to prove that a set of vectors are linearly independent. You first have to assume they are linearly dependent, okay? And there is an example here that you can actually follow through if you again watch these two videos that I've posted here. Due to time, you really need to go through this one and actually revise how to prove that not matrices, but actually vectors are either linearly dependent or independent. My focus here will be the things that I've summarized here from my linear algebra notes, okay? Because adding linear algebra will consume time. So over the years that I have gone through linear algebra, I have my notes. So this is where I took most of these and I made these summaries. So we only have solution to linear equations, okay, if the equations are linearly dependent. So they have to depend on each other for us to be able to find. So anytime you find a solution, some linear equations have no solutions. But if they have a solution, it means that those two equations or more are actually dependent on each other. It means they are coming from the same vector. So if they okay, so you see the connection between the determinant and the dependency of the vectors, etc. And this is tied together with the coefficient matrix. So these are just things for you to know before you can be able to go through some deep learning or some machine learning. So how do we tie that relationship? We tie that relationship by summarizing it here in eigenvalues and eigenvectors. So what is an eigenvalue? This one you have to know. So this is the relationship that we actually have here. If we have a matrix that when you multiply with this vector, it is also the same as having another value, which we call as a scalar is just a one value multiplied by the same scalar vector, okay, is actually this lambda that you have here. And the eigenvector, okay, is that x, that vector. So we say x is the eigenvector of A, okay, and lambda is the eigenvalue of A, okay. So it means that if I take a given matrix and I multiply it with a vector, it is just the same as taking, so that this matrix is behaving like it is just a single value, okay, a single scalar. And that brings a very, very important relationship. Not that x is equal to 0 satisfies this equation, but 0 is not an eigen value. So the eigen be a value that is greater than 0. So again, finally, I want you to check how to find eigenvalues given a matrix. Okay, you can find both eigenvectors and eigenvalues of a given matrix. And it is actually not difficult. When you follow through this and you again watch those videos that I have used to summarize. So not for cramming, but for knowledge purposes, check on that one also. And then something called the definiteness of a matrix. Now to spend more time than today on revision. So on matrices and linear algebra and vectors, you can just check them out and then you grab what you can grab so that now we start kind of. Today I want my focus to be on calculus, which is the most important in my view as far as what you are going to do is concerned. So I just want to switch to calculus very fast. And in calculus, I'm going to revise differential calculus mostly. Then you can revise integral calculus. So the notes are again also there on the e-learning. Here we are going to do a lot, by the way. So you can open these notes. Then I take you through very fast and quickly. All the way up. So today's class is meant for this, and it's going to be extremely important. So this is our last mathematical revision. So we are still on this agenda. And we are going to revisit functions, limits, differential calculus. Then you can actually check out integration, which is the opposite. So quickly, I just want to start on functions. What actually is a function? Then these are actually, now this is the heart of and soul of what we'll be doing. So functions, you know them already. They're a set, a collection of objects, mostly numbers. And in machine learning, a set is going to be a data, so we call it a data set. Then there is something called a relation that can be used to merge two different sets, okay, using some rules. So that is just a basic mathematical revision that relations are actually merging different sets. And we have put up a simple picture actually here. Normally write sets like this, okay, and the elements inside the set are called members. So the members of a set. Now, my focus is here. There are some important sets that we should be aware of. The set of all natural numbers, okay, is usually written like this. That is called double N. 1, 2, 3, 4, 5, and so on. The set of all whole numbers, so it is the same as natural numbers, 0 included. It is normally written like this, double W. The set of all integers is usually written like this, okay? There's a Z here. Then we have, so anytime you see us writing a Z, we just double Z, we mean the set of all integers, okay? What are integers? Positive and negative whole numbers are like this. They have a sign. Then the set of all rational numbers. These are numbers as fractions of integers. They are usually represented, okay, a Q. And the opposite is irrational numbers, okay? Those which are written as fractions, like pi, the root of 2, and other numbers like e, which we are going to use a lot. Then there is finally the most important, the set of all real numbers. These are all points on the number line. And it includes all these numbers combined, plus irrational numbers, by the way, because they are all found on the number line. So that's why we say that a vector spanning a 2D space, we write it like double R squared. Because anytime I draw the Cartesian plane, okay, it's like I'm combining two number lines. And in this space, I have all the numbers that can be found in a number line, positive and negative in the X and the Y axis. So anything that is spanning a 2D space, so anytime you see them writing this, they're just saying a 2D space, which is actually the graphs we normally draw. So that should not scare you. So that's all on sets and relations. So let's go into a function. I'll deal with functions all the time in machine learning. And even the whole of computing is just made up of functions. Then a function has something called the domain and the range. The domain is the set of all possible inputs, okay? And the range is the set of all possible outputs. And this is also important. Symbols that represent a number in the domain of a function are called independent variable. Okay, fine. There's something called a dependent variable and independent variable. So if you equal to 3x plus 5. Okay, so x is the independent variable because whatever x is going to affect y. So actually y depends on x. That's why we call it a dependable or a dependent variable. So if my x is 2, so 3 times 2 is 6, plus 5 is 11. Y will be forced to be 11. So y just depends on x. And this is the thing that we have here. So instead of y, sometimes we just write the function of x. Okay, so the function of x, fx, like this. And we can use any letters, but x and y, they are very famous. So we know the dependent and the independent variable. That's going to be important, especially next week as we start on something. So the function, lowercase always, it can be f, g, etc. Then it has a formula. So example here, we have a function like this. Plus 1, x is independent. So what output? So that's how we define a function. Then a function has a domain, so you actually read about the domain. Okay, some domains are valid, some are not. So example, in this function here, the number 5 cannot be part of the domain because it leads to division by 0. So if x is 5 in this function, 5 minus 5 is going to be 0. Then 3 divided by 0 will be undefined. So this function will not have a value when x is 5. So what happens is that x is equal to 5 is kind of excluded from the domain. So we say the domain of this function is all real numbers except x is equal to 5. So x can never be equal to 5 as far as this function is concerned. That's how important the domain is. So if you draw this graph of this function, at the point x is equal to 5, this graph will be distorted or discontinuous. So we have more examples here. Recall the range. The range is related to the output. It's a set of all possible outputs. So some functions cannot produce some values. That's just the way it is. For example, f of x is equal to x squared. It can never produce negative outputs because you are getting the input and you're squaring it. So even if x is -2, -2 squared is still a positive number. So it is still equal to 4. So when I draw this graph, you see this is the graph of the function. It looks like this. So it means that the moment I look at a graph, I can know the domain. Some values will never be obtained from this function. That is going to be extremely important. Look at the function fx is equal to the sine of x, okay? Sine of x, the range is between 1 and -1. The domain is infinite. You can have any number. You can get its sign. But the sign is bound between 1 and -1. So for us in machine learning, we are going to use the term, it is bound. Sometimes we'll be looking for functions which are bound within a certain range, okay? And that will depend with what we actually want to do. So these are just examples of range. This is revision. So quickly, types of functions. We have different types of functions: polynomials, exponentials, logarithms, trigonometric, and all these are types of functions that we will be dealing with. Very quickly, polynomial functions, their definition is here. You can check them out. And then we have examples here, down here. So you can actually start to see the shape of these functions like polynomials. Okay, so in a polynomial, there is an order. Okay, it can be linear. Then we have linear functions, which are actually now polynomials, and you see how they behave. The most important thing I can point out here is the gradient or the slope of the function, which tells us how the line is kind of flowing within the space. So if m, so m here is the gradient, okay, slope is rising, okay. If m is greater than 0, the graph is rising, okay. So you see this graph, we normally move from this side going to this side. So this graph, so anything that looks like this has a gradient of greater than 0, okay. Then this other one is missing, so anything that flows like that, the gradient is less than 0. Then we have the y-intercept and the x-intercept. The y-intercept is the place that the line actually cuts the y-axis. Okay, so for this one, the y-intercept will be here. So at the y-intercept, x is always 0. Okay, and at the x-intercept, the value for y is always 0. So then we have quadratic functions. You can check them out, still the same. Exponential functions are more interesting because they look like these. So for the exponential function, whereby you have a base, this base is a variable and the index or the power is, no, the base is a constant, the power is a variable. So the y-intercept of all exponential functions is always 0, 1. Okay, it will always cut the y-axis at point 1 for all exponential functions. And there is a reason here. Because a number raised to power 0 is 1, okay, we say that in the y-axis, in the y-intercept, x is always equal to 0. So we just usually ask if x is 0, what's the value of y? So you substitute that 0 here, you actually get 1. So all exponential functions, they pass at 0, 1. Then all exponential through point 1a, because a number raised to power 1 is that number. So this makes it easy to sketch any given exponential function without having to plot all the values. You can actually be able to sketch. So even if I was to sketch the curve of y is equal to 6 as to power, it is very easy to actually sketch that one. These ones are called exponential functions. Logarithmic functions are the inverse of exponential functions. So we just change everything. All logarithmic functions pass through point 1, 0, and a1, and they're the inverse. Okay, so you see it's like the opposite. How do we define logarithmic function? It's defined like this. Y is equal to the log base of a of x. Okay, so logarithmic are the inverse. Then we have some other funny functions like rational functions. F of x is equal to 1 over x, or the inverse of x. Look at how this function looks like. The function is discontinuous here. Okay, there's a discontinuity here. So it is kind of divided into two. These shapes are going to be important in machine learning. Look at the graph of 1 over x squared. It is kind of misbehaving like this, going all the way to infinity, all the way up there. So all rational functions, they are discontinuous for those values that make the denominator to be 0. Okay, and you can actually check those ones out. Radical functions again here, and different types of functions. The absolute value function, look at the shape of this curve. So the shape is actually very important. So for example, here, if I say find f of 2, okay, so when x is 2, this function just say absolute 2, which is actually equal to 2. If I say find f of negative 2, it's equal to absolute negative 2, which is actually equal to 2. So absolute means that you just count, you ignore the direction or the sign. So when x is negative 2, you see y is still 2 up there. That's what gives this function that funny shape. Then finally, we have trigonometric functions. These are going to be extremely important functions. So let me summarize them here. It not have opened in the way that I wanted it to open. Let me get PDF. So for trigonometric functions, I want you to focus on a number of stuff. Why is this important? Some people will be analyzing audio data. You will actually be dealing with trigonometric functions. So I hope you remember the trigonometric ratios, which again, you don't have to cram. You just have to be aware of. Sine is usually opposite of hypotenuse, blah, blah, blah. And then there's the opposite of sine is known as cosec. Opposite of cos is known as sec. Opposite of tan is known as cot. And then these are just the inverses. So for example, sine is opposite of a hypotenuse. Then cosec is the inverse of sine. So it is hypotenuse of a opposite. Those are called trigonometric ratios. There's 6 trigonometric ratios. There's usually a triangle which you can use, and you can actually check here the table and how to convert degrees to radians. And there's something called a unit circle. You might need it when analyzing audio data or any data that has waves. So machine learning is multidisciplinary. Sometimes the data has waves, and these are the things you'll be analyzing. So again, you check here about the amplitude and the period, and you can actually see there is a range to this that we actually have here. So these are the 3 main trigonometric ratio graphs. The graph of y is equal to sine x usually looks like this. That is one period. Okay, the period is the moment after which the graph just repeats itself. The graph of y is equal to cos x looks like this, and tan misbehaves, so it looks like all these 3 different things. Now, my focus is here because these functions, we are going to use them in machine learning. They are called hyperbolic functions, okay? Hyperbolic functions. Now, there are 3 hyperbolic functions. This is called hyperbolic sine. You don't have to cram it. You just have to know it exists. So these are the shapes of these hyperbolic functions. So the first one is the sine of x. You see it here. And then this is being compared to the hyperbolic sine. This is the graph of hyperbolic sine. Then hyperbolic cosine or cos, okay, has this formula. And then you can actually see how it appears here. But now the most important is going to be tan h, which is called hyperbolic tangent. We are going to call it tan h, which is the same as hyperbolic sine divided by hyperbolic cosine. And it's just those 2 formulas combined. Okay, so it gives it this formula. Now, because of the shape of this tan H. Parabolic tan, guys who are looking for a graph or a function that has this S kind of a shape, then hyperbolic tan actually has that shape. I told you the shape is one of the most important things here. So even though tan misbehaves like this, but hyperbolic tan looks so smooth and in a nice kind of type of a function. And you can actually read about translation, reflection, and scaling. So I can scale one function in order to get another function. So to wrap it up on functions, we have different types of functions, from polynomials to trigonometric, and we will be dealing with all these types of functions. Then you can have one function being changed into another function, etc. So for example, if this is a wave thing like this, okay, then this wave, it can be amplified or it can rescaled, okay, such that now it's a bit larger like that. These are the geometrical transformations. Okay, so you actually see we have now formed a new function. Okay, and we have increased the range by a given factor. So sometimes I don't need to cram the function. I can just transform one function into another, and that's we are going to use that also. And function, the limits of a function. So what is a limit? Now I'm going to summarize what a limit is, and this is extremely, extremely important. So if you can get it, please do. So the limit, now we are going to do the number one, we have said we have a dependent and an independent variable, okay? X is usually independent, then Y is dependent, okay? So when we have, or when we are finding the limit of a function, okay, like it says here, we are going to ask ourselves, as X is approaching some given value, okay, so X is tending towards some value. So as X tends towards some value, to which value does the function tend towards? Okay. So if X is moving towards number 2, closer and closer to 2, this function, it's getting closer and closer to which value? Why is that important? We are going to see. So as X, which is the independent variable, okay, it's tending towards some value. What is the function, or what is Y, the dependent variable? Because these are the same. What is Y tending towards? And that is the maths of the limit. So we normally write that one like this: limit of function X, okay, limit of the function as X approaches C is equal to L. So L is the number now here. L is that number that is actually here. And that is actually what limits are. So the limit of a function is going to be extremely important. And I have summarized something down here that is not opening on my board. So having known what limits are and what they try to find, please revise how you are able to find limits. Okay, how do I find limits of a function? I try to approach from the lower side and from the upper side, and if the two are equal to each other, then we are actually going to say this function has a limit. Sometimes the limit does not exist, okay? And we are going to say limit does not exist. So here we say example, there is a function x squared minus 25 divided by x minus 5. We are meant to determine the limit as x is approaching 5 if it exists. So actually, how do you find that one? So this is revealed. Is the limit as x. So we're asking ourselves, as x is approaching number 5, what is y approaching? Or what is fx approaching? Which value does the function approach? So as x approaches 5. So how do you do that? They normally say you just kind of find a range. So we go one step 4 and 5, then we go one step higher, 5 and 6. Okay, then we approach 5 from this is the lower side, and from the higher side. Then we check if they are converging to some value, then we will say that is the limit. So the easiest way is to do a table. So you see these are the values of x getting closer and closer to 5. So we started with 4, see 4 here, then we increase a little bit, 4.235, then we go to 4.9, then we go to 4.9999. This sign here means that don't give it a 5. Okay, so it is the limit as x is approaching, but never get to 5. So as x, when x is 4, what is y? Just substitute this value to the function squared minus divided by 4 minus 5 and 9. Also, all these values. Here we are meant to start with 6, started with us. So you're going from 5 point to 5.0. The lower side. Then we see that here, like when x is approaching 5, okay, the function is like the function is approaching the value 10. So we say the limit of this function is 10, okay? How do we interpret that? As x is getting closer to number 5, y is getting closer to 10. That is going to do like a lot in what does the dependent variable tend towards. Okay, sometimes the limit does not exist. You can check out this example. We try to follow from below and from above, and then we saw this is 8, this is 11, and then we normally just say D and E. That's just swag in math to say that does not exist. Good. As we won't be calculating this in the CAT, we are actually doing this in order to do the next segment. Julie has a question. How do we come up with those other values in the table? Which values? The x and y's. Like, for example, if I understand your question, for example, let me go back here very quickly. I don't want you to cram this, but to understand it, good. So how do we come up with 4, 4.2? You just guess these numbers. I could just start with 4, okay, provided I start there. Then I get closer to 5. The next value I could say 5, yeah, closer to 5. So finally, just ensure you have 4.9. But don't become like, don't make life tough. Don't have like a million nines here and then you want to know now. No, it's an estimation kind of a technique. Okay, it's an estimation. Okay, fine. So Julie is okay now. So In case you have any question, feel free to call. It's not a mathematical class, it's revision. So very quickly, we know what limits are. That's the main thing. I want you to know what a limit is and maybe how you can get a limit. Then you can read here how to get all these limits, okay? You can just revise of polynomials. You just directly substitute. So for example, here you just take this one, it will give you the limit, okay, for polynomials. And you can read all these principles. I want to go through these ones. There's another one called limit to infinity. Okay, so the question here is that as x gets very large, okay, it's tending towards infinity. Okay, so the question here is that is answered by the limit. Which value does y get towards? What does y approach? As we get closer and closer to infinity, as x becomes very large, what does y become? Okay, and you can read here and actually be able to see. There's an example here. If the function is 1 over x squared, okay, so as x is getting very large, it is going towards infinity. Okay, what does y go towards? Okay, and you can just investigate always. So we don't write this, we just write, so we don't write this, we just write the limit. Okay, you already know this. X approaches infinity, okay, of function f, function x. Function x is what I'm using as y here. And then this is going now to be here. Okay, fine. So we can plug in some numbers and actually see 1 over 1 squared is 1. 1 over 10 squared is this number. So the number gets smaller and smaller and smaller. So we can just conclude and say the limit x approaches infinity of this function is equal to 0. It means as x is approaching infinity, then y is getting closer and closer to 0. It's approaching 0. Okay, that's the definition. So finally, I think now I'm done with limits. The rest is just revision. Okay, so the reason why we did limits is that it will lead us here. And so I don't want you to fill your head so much with the limits. Now I want you to fill your head so much with this one now. Fine, so differential calculus is the branch of calculus that converts limits into differentials, okay? So the idea here is that we can be able to find the rate of change. Again, I want to explain. Have it behind, not behind, have it at the back of your head that there are two things here, okay? Number one, in functions, that is, there is something that is called an independent variable. That is something that I want you to stick this week, next week, and always. Okay, there is an independent variable. Independent means free. It's on its own, normally an x. Then there's a dependent variable. Dependent variable is always waiting. It will depend on the value of x so that we can know what y is. So what is the rate of change? Okay, it refers to the change of one quantity. Differential calculus, this is what it studies. Okay, how does y change when x changes? Okay, if I change x by 2, what will be the change on y? Okay, that is differential calculus summarized. So you actually see the knowledge of limits is actually very important because it's related. We will get to a point whereby next week as we start, where the independent variables can be more than one. We'll have x1, x2, x3, etc. But the dependent variable will always be one, a single one. Anyway, very fast, you can revise these ones, how to get the difference between two on a curve. There is a graph here that can help you through. If I have 2 points, P1 and P2, I can actually get the distance along that line, okay? Remember, we were just doing, and this was the gradient, by the way. If I have coordinates x1 and y1 for the first point, let's say that is for P1, and then I have x2 and y2, let's say that is for P2. So these are just points in this graph. So to get the gradient or the distance, etc., we just normally used to subtract, okay, this and that divided by the subtraction of this and that. Okay, that's what is kind of happening here. Okay, that is what is kind of happening here. Yes, someone is calling in. Let me see. Okay, fine. So very quickly, so this is not something you spend a lot of time in, but when you're revising, I want you just to pay attention to calculus because it forms a lot in the foundation. So you can look at all these. Now, out of all these, the kind of equations that are formed here, and this thing called a h, which is the distance between this point and that point, is where now finally we form this equation, okay, the limit, so you can actually revise that one. And then we are able to get now the differential formulas. So I will skip this point. I won't derive how you move from here to here, but it is something that I will want you to just check and be interested in. My summary is actually here. The average rate of change is the secant line. There's something called a secant, but the instantaneous rate of change. So there's the average rate, this one that I've just explained. Then there's the instantaneous rate. The instantaneous rate is the rate at a point, which is going to be our focus. Is defined by another line called a tangent. So as we will be interested by the rate of change at a point, okay, a particular point. So to be able to do that, we are not going to do up there, but this is how we get the formulas for doing differential calculus. This line is going to be twisted, somehow transformed until it sits so well on this point that we're interested in, like so. And this line is what is called the tangent line. You don't have to cram that one. Okay, tangent. Good. And then this line, the slope of this line, the slope is going to define the differentiation of that, of this curve, the original curve, of which I won't spend time in. So from here, I want you now to move all the way down here. I won't go through that example. I will go exactly right here. So good. So these are the rules of differentiation, and they are going to be important. So this is what we are going to revise today. Then we finish. We'll finish early, so please don't ask for a break. We're just having fun as we revise. We have not yet started, so no cramming. It's relaxing and focusing. So the rules of differentiation. Rule number one, when I differentiate a constant, it's a zero. So anytime we are finding differentiation, they can be written in any format this way. It can be y prime or f prime of x or dy dx, and any of these signs, okay, just means find the differentiation of y with respect to x. In other words, when we change x, how does y change? Okay, that is the thing. Fine. So someone's mic is on. Good. So these are the things I want you to pay attention to. Number one, when I differentiate a constant, like you are given this function, then you have to find dy dx, or the differentiation or first order derivative. The answer is 0 always. Then there's something called a power rule. If you're given a function like this one, y is equal to 3x power 5, you just say 3 times that power, okay? And then, so the formula is here. This is the formula, okay? So k times n, x remains. The power is, you subtract 1 from the power. So the differentiation of this one becomes 15x power 4. Okay, so 3 times 5 is 15. X is 5 minus 1. And we all know this from high school to our mathematical units. Good. Rule number 3, the derivatives of polynomials is done term by term. Okay, so you just do term by term. That might not be clear here, so switch to this one. Okay, so term by term. So you can focus on that slide. Okay, fine. Rule number 3. So differentiate this function x squared into 4x minus 3. Okay, you can open the brackets. So 4x cubed minus 3x squared, this is a polynomial function. Okay, so the dy dx, you just deal with this term and that term. So this term is actually 4 times 3. Remember the power rule, x 3 minus 1, so it is going to be 12x squared minus 6x. These ones are easy. We can close our eyes and actually do dy dx. The product rule, now this is where it all starts. If I have two functions like these, two functions being multiplied together, this is the what is called the product rule. You take the first function as it is, you multiply by the derivative of the second function. Okay, you can put brackets here. Then you add the second function, multiply by the derivative of the first function. You kind of interchange. That is called the product rule. The product rule. That is going to be extremely important in finding a lot of derivatives. So for example, if you are asked to do the following, find dy dx, or the y prime of 7 minus 3x brackets, and then 3 minus 5x brackets. These are like two functions. So you can actually use the product rule here. Okay, so the product rule, please have it in mind. And I've organized my calculations like this. First function, it's derivative. Second function is derivative. Then I'm using now the knowledge of the product rule, and after multiplying, I get now dy dx is equal to this one. Okay. Then rule number 5 is called the quotient rule, another important rule. If I have two functions, okay, and there is a division here, y is equal to first function divided by the second function, then the derivative is this denominator function, the derivative of the upper function, numerator, minus the quotient rule, very important again. So y prime of 3x5, 3 minus 5x. Okay, again, I do like a table. Then I combine them in that formula, and then finally I get this one. Sometimes you don't have to simplify further. Then finally, another important one is called the chain rule. Okay, so if I have a function in this format, okay, there is a constant and then the function raised to a power, then I can just open it up like this. Okay, I can have k times n the power. The function remains n minus 1 like we have the power rule, but now remember to multiply it with the derivative of the function again. So that can help us to do things like this one, okay? So to do something like that, again, a table can help me, and then I will end up with the answer like this one that I have here. So now, then finally, you can be able now to combine the rules. Okay, so here automatically it's like we will use the quotient rule, okay, from the look of things, because there is a division involved. But now when we are dealing with this bottom side, okay, we have to apply the rule, another rule again. So you actually see how we have done this function, okay? So there are many ways that you can be able to do a function and then finally end up with a given answer by combining the different rules. So you actually see some derivations are actually a bit tricky. So by combining all the, by going through all the processes, just want to give you a, and then after that, we finish on the derivative. So find a few examples on calculus 1. You are able to try them so that I see if you can remember. This is going to be the most important, by the way. The most important applied mathematics, calculus here, calculus 1. Okay, fine. Product rule, trigonometrics, I'm going to deal with those. Okay, fine. So I want you to try this one. Let me repeat. No, let me snip it this way. The board. Sorry. Okay, fine. Just a moment. Return the pen. Do the paste. Yes. And yeah, true. So I'm not sure if you can see that one. I want you to take some time and try to find dy dx, what you're looking at. Okay, I don't know what this pen is. Find these two. You apply all the rules that you know. We can check the notes, and then we can be able to continue. Okay. The first one, what is the derivative of y prime? And which rules did you actually use? So actually here you can call in either the first one or the second one. The second one is very easy, very easy. I'm going to use the product rule. And you don't have to simplify it to the farthest. After applying the rules, you can leave it like halfway. Yes, anyone with an answer? Maybe today we can start with Rebecca. Still calculating. Okay. Manual, let me see. Quite a number. Edmond, any feedback? You can hear me. Yes, Isaac.
Okay, for the second one.
Yes, the second one is easy.
I used product rule.
Yes.
So the first function for me was 6x cubed minus x.
Yes.
And then for its derivative, I got 18x squared minus 1.
Yes.
Then the second function was 10 minus.
No. Wait.
Yes.
18x squared. Yes, minus 1. Yes, minus 1. Good.
Then the second function was 10 minus 20x.
Yes.
then its derivative I got negative 20.
Yeah,
So
true. Then now combining the two.
yeah, so combining the two, okay, I didn't do it to its simplest form. I just got 6x cubed minus x multiplied by negative 20
Okay.
plus 10 minus 20x
Yes.
multiplied by 18x squared minus 1.
Yeah. True. Okay, then you notice that when you open the brackets, you'll be able to get something there.
Yes.
Yeah, true. Very good. So yes, actually the product rule and how you use it. Thank you, Isaac. Julie, also your hand was up. Same. Second one.
Yeah, it was the second one.
You have the simplest form.
Yeah, I have the simplest form, which is
Okay.
negative 480x cubed
Negative 480x cubed
plus 180x squared
180x squared
plus 40x
plus 40x
minus 10.
minus
Yeah.
10. Okay, fine. We'll be checking that one in a moment. Thank you very much.
Welcome.
Good. Okay. Anyone with the first one? Yes, Vanessa.
First one, where
Yes.
the first,
You have the simplest
yeah.
form. Okay.
So the simplest form is negative 4x cubed
Okay, negative 4x cubed.
6x squared,
Plus 6x squared.
all of it divided by 3
Okay, divided by 3.
to brackets x squared, x cubed,
X cubed. Okay.
Raised to power 2 over 3.
Raised to power 2 over 3.
And then into brackets 2 minus x.
So what is in the bracket? Everything or just the denominator?
Just a denominator. Okay. So let me just type it in the chat.
Okay, fine. Thank you very much. Okay. So even before Vanessa types, I know I'll get a maths editor that we can actually share by the entire class, so that it's like someone going to the board and actually writing. Okay, fine. That's very good. Just pull it here. I just pulled it from the calculus. Waweru, yes.
Oh,
You have a feedback.
yeah.
Yes.
Yeah, this
Yes.
is what I got. I got
Yes.
negative 2x cubed.
Negative 2 cubed. Okay.
Plus 10x to the power of 2 over 3.
Okay, that's the second one.
First.
The first one.
Yeah.
After simplifying everything. Okay, fine. Okay.
Yeah, but yeah,
yes. Okay. Thank you. Okay, thank you very much. Vanessa has already typed. So the denominator, yes, x power 3 raised to 2 over 3. Then there's another bracket, 2 minus x into 2 over 3. Okay, fine. So you notice that, so let's just pull. There are some solutions here. Then we check, then we see. Okay, fine. So according to the book, get this is the first one. Okay, yes. You see, it's quite a long calculation. So okay, let me see the equivalence here. So actually, the idea here is that 3. So it's the same 2/3 here. Then you use the product rule to strip the two functions like this. And then you keep on expanding until you get somewhere closer to this. So let me see the similarity. Vanessa, which rule did you use?
I used the chain rule.
The chain rule. Let me see if the chain rule applies here. Why did you use the chain rule?
Because, okay, I assigned the square root, the first square, what's it called? The cube root as
Yes.
fu, and
Yes.
then the second part, I mean, as f, and then u as x squared 2x minus x squared.
You substituted some other letters.
Yeah.
Okay. I see where it's coming from. But now when you use the chain rule, actually the power here is 1. Okay, because like this is like the main function here. Okay, fine. Okay, thank you. But it will be easier now to use just to view these as two functions, okay, and just try and use like the product rule. But whichever rule you use, sometimes you just find yourself like flowing, etc. So the idea here is that when you see like two functions like so, you can actually just directly move to the chain rule. So now, yes, Vanessa. I saw your hand up, or you're
I
fine.
tend to take it down.
Okay, fine. So now, for example, here, there are two functions. So I can use the product rule, that is the product rule, or I can just open the brackets. Then I do just like a normal polynomial. Anyway, these ones you just practice so that you're familiar. So we won't be testing that one, but we just want to know how to compute derivatives of certain functions. But I told you that in the assignments, assignment 1, mathematics for machine learning, I'll just give you some of these things so that you practice and then you submit and then you'll be good to go. Anyway, those are the rules up there, and I'll give you questions which you'll submit as assignment 1 that will cover from probability all the way to calculus. So very quickly, let's look at special functions. These are like special functions. There is what we call the natural function that has a number that is normally called an E. E is called the Euler's number. Then there's a special function that can be used to describe E. It is usually this one, 1 plus 1 over n raised to power n. You see I plotted the graph here. So as x, my pen, as x tends towards infinity, we can see here, as x is growing, y tending to approach this number E. Okay, so the curve tends to get closer and closer. It never touches this line, but it gets closer and closer. Okay, we call that the a natural exponential function. So what you need here, this is now like the main things here, is how to do derivatives for these special functions. And examples are actually there, but we start right here with this first rule. The derivative of e raised to power x is always e raised to power x. So if you're told that derive the following function, y is equal to e raised to power x, you don't go into a lot, you just say y prime, it is still e raised to power x, okay? And that's going to help us a great deal. That's the first rule in these special functions. Then the second rule here is that if e raised to power, so if e is raised to a function, okay, the derivative, we are going to open it up like this. For example, derive y is equal to e raised to power 2x. Okay, this is the same as doing the derivative of that function that is found at the top there, that is 2x, okay? So the derivative of 2x, we know it's 2, okay? And then you multiply that by whatever you were originally given. So that example is easier to follow when you have examples like these ones. Okay, so you look at this example. So the answer to this one will actually be the derivative of 2x, which is 2, multiplied by what I was given. So the derivative becomes this one. Y prime is equal to 2e raised to power 2x. So these ones again, you just go through them and practice, and then you are able to see. Then finally, not finally, but quickly, I move down here. Note that y is equal to e raised to power x is called the natural exponential function, and it's going to be important. Remember, exponential function, they always pass through at this point, okay? Now, logarithm to base e are usually called natural logarithms, okay? And they are usually written like this, ln, okay? So you must remember this, it's going to always appear, that when I say the natural log of x, I actually mean x to base, log to base e of x, okay? So ln, natural log, is log to base e, okay? And what is e? E is that long e number that we talked about. So the derivative of exponential functions, you also go through this, okay? Find the derivative of y is equal to 2 raised to power x, okay? This is the same as just multiplying 2 raised to power x and getting the natural log here. So here is we need to focus. So suppose y is equal to a raised to power u of x. This slide never opens well. A is a positive constant, etc. So you go through this. Okay, so the derivative multiplied by the natural log of a. But now you have to remember that the natural log of e is always 1, because we mean here log to the base of e is actually equal to 1, because e raised to power 1 is actually just e. So now examples to be able to familiarize yourself with all these special derivatives, okay? You can look at more and more examples here. The derivative of natural logarithmic functions is the same as taking the derivative of the function divided by the function itself. So if you're given something like y is equal to natural log of 2x minus 3, okay, you will take the derivative of able to sort a lot of issues this way. Fine, so I won't spend much time here. How the power rule is actually used, and the product rule. These ones I've made nice notes so you can follow through. My next stop will be the derivative of trigonometric functions, because we can't control the type of data we'll be handling. And when we are handling waves, we will actually have to know all these derivatives. So we are not computing them, we are just summarizing. The derivative of sine x is usually cos x, okay? The derivative of tan x is usually sec squared of x. And you can look at all these and be able to see. When I get the first derivative of cos x, I will always get negative signs. And you can look at the rest of the formulas from here. As it means that we can do a number of questions, even by not going into so much details. So, for instance, if you're given that example there, please look at that example. Differentiate the g of x is equal to 3 sec x minus 10 cot x. Okay, you will try this one by looking at this. Okay, I did the second one. Find the first order derivative or p prime. So here we can always use y's and p's and t's, any letter, but we normally use x and y. But now we are using p here. So p is 5 sine x cos x plus 4 cosec x. So for this first term here, we use the product rule, okay, just like we were doing. And I use these rules here, okay, to get the derivative. Then I'm able to finally, I get this, which I don't simplify further. And this now is the answer. So trigonometric functions are also very important. You will always be working with these rules if we ever encounter trigonometric functions. Maybe we need an audio wave to change into another wave, etc. And that would also for hyperbolic functions, those rules will actually be. So now we are going to take just about 10 minutes, and now this heart of calculus is going to help us now solve some very, very key problems in machine learning. So we call that section applied derivatives, okay? First, I know how to compute the derivative, then I actually use it. So how can we use derivatives? So quickly stick with me, we'll be done in a moment. So I first start by discussing high order derivatives. This is very easy. For example, take this function, okay, and then I ask you derive this function or differentiate this function 4 times. The first time we will get 15x squared. We already know how to get that one, minus 6x plus 10. Okay, that's called the first derivative. Then if this one now, my answer, I get the second derivative, x minus 6. Okay, then if I derive this one, I get the third derivative, which now is 30. Okay, then if I do the fourth derivative, now I get a 0, because when you derive, when you compute the derivative of a constant is actually a 0. We call this the high order derivatives, and they actually here you must pay now attention to train our neural networks, and also the way we are going to train regressions or regressors, and the way modern day deep learning actually works. So this is, I'm going to mention them right here and right now. So first order derivative and its sign can tell us where the curve is rising and falling. That's going to be important, because in machine learning, when we want to reduce the error, we want to look for places in the loss function where the curve hits a minimum. Okay, that's going to be so interesting in our case. So where the curve is rising and falling is going to be a point of interest. And you can actually look at the diagram here. So if the first order derivative is less than 0, okay, the curve is falling. If the first order derivative is 0, the curve is flat. If the first order derivative is greater than 0, the curve is rising. And you can actually see all these places on the curve. So even without plotting the curve, we can do our computation by knowing at this place, the curve is rising and the curve is falling. That's the first thing. So if we wish to find the range of values for which the function is increasing and decreasing, we look at the positivity and the negativity of the first order derivative. So if you're summarizing, the first order derivative can be able to tell us where the curve is rising and falling. Then number two, there are some things called critical points. It is where the first order derivative is zero, okay? Or the first order derivative is undefined or does not exist. Very good. Not for cramming, to be applied from Monday. Now I move to optimization, act of trying to find the extremas of a curve. This can be the minima, okay, which is the minima and the maxima. This is going to be the heart of training or of learning of many models. So read here what global minimum and maximums are. There is a curve here trying to illustrate how to find, no, not how to find, where actually they are located. There's an illustration here. I want to point out the following. The extremas. We have two types of extremas, the local and the global. We'll be interested in these things. Okay. So first order derivative has information on how we can find the extremas. Okay. And you can read here, if the sign of f prime of x, which is the first order derivatives, changes from negative to positive. Okay. And you can actually read these 2 points here. They're actually very important. If the curve, the first order derivative changes from positive to negative, it means we are going to feed some values here and then try and check, how is this derivative behaving? Is it changing from negative to positive? Then we can actually know how to get the maxima and the minima. There's an example here. Please do this example. The questions I'll give you, they will test these ones, okay? And actually you're able to see. So first you get the first order derivative, it's here, 3x squared minus 12x. That one we know how to get it. Then to get the critical values, you're going to set this first order derivative equal to 0, like this. Then using your knowledge of quadratics, okay, equations, you will get the critical points by solving that equation. You'll get the first critical point is when x is 0. The second one is when x is 4. Okay. Then after getting those two critical points, these are the points of focus. Okay. These are the candidates of where the minima and the maxima are. That's going to be important. So why is 0 important? Because the actually get the slope of the curve. And when the curve is flat, there is no slope, okay? So you can write, there is no slope on a flat curve, okay? So actually these places where there is no slope, these are the places of interest. This is where either our minimum value is hit, okay, or our maximum value is hit, okay? Those are the candidates. That's why they're called critical points. And that is extremely important as a summary from calculus. So these critical points, you can find them this way. There's an example here. So first order derivative has some information. Now, what information does second order derivative contain? Now, even our point of interest. So if the second order derivative is greater than 0, then that is the local minimum, okay, at that particular point of C. If the second order derivative is less than 0, that is the maxima, okay? So you can actually see less than is the maximum, it's like the opposite. Greater than is the minimum. Notice with second order derivative, we now avoid the number line and so many tables, okay? So you can actually see how I did that. After getting the critical points, I just fix, you see C is a critical point. So I fix my critical points here, okay, in the second order derivative. So the derivative of the function given above is this one, 6x minus 12. And the critical points are 0 and 4. So I just fix 0 here first. Then I find the value. If I fix 0 here as 6 multiplied by 0 is 0. So I remain with negative 12. It tells me that the local maxima is hit at this point. If x is 4, fix it here. Then I hit at 12. Then I say this is minimum point. Okay, so the second order derivative carries more information about how to get the minimas of a graph. Okay, fine. So read where we can't use second order derivative. And then finally, how to get the global and the, yes, global maxima and the minima. These ones you can now revise as you go through more examples here. And very final one here is how to find the points of inflection. I will again summarize. So we have our curve, like normally drawing an S, like this. Then let's say the curve continues, and so on. Okay, so there's a here. Okay, there's a minimum point here. Let me get a different pen. Then there's a maximum point here. Okay, there's a maximum point here. But now the point of inflection is somewhere here, where the curve, so you see from the minima, the curve starts rising. Okay. Then after it hits a maxima, it starts falling immediately. Okay, it's falling. But now there is a middle point always, because this curve is going to fall somewhere. Somehow, there is a point where this curve stopped rising, and then it started falling. Okay, that's the point of inflection. The very point, and it's usually hidden, you can't see it most likely. There is a point here where the curve, the rate of change, from rapidly rising and it started to fall slowly, 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 then faster, faster, faster. And that's the instantaneous rate of change can help you to get the point of inflection. The exact point where this curve stopped rising and started falling. And at the point of inflection, the second order derivative is 0. And you can actually also revise that one. Is going to be of interest for us as we start training the models. Good. So fine. Yeah, there are more examples here on how to find the critical points, point of inflections, and maxima and minima, either global or local. And these are summary, a very quick recap that we have just done on differential calculus. You can revise integration or integral calculus, but not much. Maybe we can revise if we need it, but differential calculus is what is mostly used, especially when we are training our networks. So that is where we wrap, finally, that's where we wrap it up. Of the revisions. So now, just a very quick recap. So if I may go the way back here. Fine. So we have actually talked about this from last, okay. So this one, and today we just finished trying to understand statistical machine learning, etc. Now on this application actually is what we are going to apply as we go through. And also on Monday, I'll be able to talk about the labs and the lab preparations. So actually to help you to recap and revise well from all the things that I've been mentioning, I'm going to upload some questions, I think by tomorrow. So check e-learning by tomorrow. It will be individual assignments, calculations, mathematics for machine learning. Then I will also give you the date to be able to submit. That will be our assignment for revision. So on Monday, we begin immediately on the following. So what are we going to do on Monday? We are going to do the following. So from the outline, we are going to do computational learning theory. Okay. And I told you I'll be combining the works of week 2, 3, 4, and 5, 6, and 7 interchangeably. Okay. The next place I will be jumping to is here. Okay. So you don't want to miss it as we start. You also want to prepare your devices, ensure you are good to go. We'll be working online anyway. So, but still you can install all that you can. We'll be using Google Colabs, and that's why we'll be coding from Monday, immediately from Monday. So Monday, I will want to look at learning theory, okay? And I will combine that with regression, linear before there's a link, so you also check on that link. It's there on e-learning. Then part 2 of the assignment will be on the documentaries that I posted. So again, there I will set something. So you need to watch all those documentaries, etc. Very fine. Is there any pressing issue, any question as we prepare to meet on Monday? There being none, I think we can end it there and rest, and be on the lookout for the questions on e-learning. Anyway, I'll send a WhatsApp message, and then that will be enough. I see guys already commenting with their numbers. This is always also another way to just know that you're there with me. The other ways to check attendance, but I like this one. So please just comment so that I'm also feeling nice that I'm not lonely. It's tough and tough times. Take care, stay safe, and yeah, we'll always be there to help. Thank you very much. Enjoy the rest of your day, and we start officially on Monday. Thank you.